I did my undergrad at Cornell in chemistry, and then I worked a little bit in industry and oil and gas at Motiva, which is a joint venture between Aramco and Shell. And I
Sure.
worked at this integrated refinery and chemical plant, which is super exciting, just to see huge pipes moving gallons, barrels of material.
Yeah.
I then left that to get my PhD at the University of Washington, and then that ended right around COVID. And then I did a postdoc at Stanford, which is where I met John, my original co-founder,
Yeah.
and we thought we'd give it a go because everyone was doing it, and it yeah, and things have moved so quickly since then. But we started work in
Yeah.
November of 23. Sorry, no, we were founded in 22.
Yeah.
But then we submitted some grants, and then we went dormant. We went back to our day jobs,
Hmm.
and then in July of that following year, we got notified in 23 that we were awarded both an NSF Phase 1 and an ARPA-E combined Phase 1 and 2.
Yeah.
And then Innovation Crossroads, which is a DOE kind of sponsored incubator for hard tech companies. So that all happened around the same time. We didn't have a facility out in California, so we moved out to Knoxville to be close to Oak Ridge while we were going to be
Yeah.
part of that program. And so we opened our doors. John and I are both chemists,
Okay. All right.
synthetic polymer chemists more
Okay.
specifically. And we had both been kind of working on sustainable, recyclable plastics. So plastics that we could more easily break down at end of life and or reuse in some way.
Sure.
And John's research really was focused on making these really strong engineering plastics that were also recyclable or degradable in some way, which are features that seem kind of mutually exclusive. And when I first joined that lab as a postdoc at Stanford, I got the wonderful opportunity to work with him just to get integrated into the lab. And it turns out that we worked really well together.
Tell us about the technology. You have two machines?
We have one, I'd say we call it with one machine, and
Okay.
it's kind of disassembled right now. But
Okay.
so we're kind of rethinking some of the concepts and how we implement this process. But the machine is kind of like you can think of it like a portal. On one side it's all uncured feedstocks, and on the other
Hmm.
side it's completely cured and formed material. And we call it Pultrusion meets 3D printing because it's kind of like it's like Pultrusion. We go infinitely long. We use
Hmm.
continuous fiber feedstocks, but like 3D printing, the shapes are digitally defined. It's a mold-free process. We just load a file, and then as we're kind of pulling this feedstock through this plane, it gets shaped and set simultaneously.
Okay. Waiting on the screen. This is an airfoil. This is an example. Is this one of the projects that you guys were highlighting at JEC?
Yeah, that's a foil that we made from a file to finish part
Okay.
nose poster in about 25 minutes.
As you mentioned earlier, it's like a combination where you're pulling like the pultrusion method, but you're molding. There is no mold. You're molding it as it's being pulled through. So,
yeah, I think there are some versions of this. Obviously, and Pultrusion exists, 3D printing exists, and then continuous fiber steering is kind of like in between, but you're kind of doing individual toes. But I think when we first started, we asked very simple questions that we didn't know. Like, for example, like even for continuous fiber steering or even fused deposition modeling, we were like, why are the nozzles always circular?
Yeah.
And that seemed like such a silly question. But when we really dug into that, we learned so much about kind of the physics and chemistry that happens in these processes that requires it to be circular.
Mm-hmm.
And so and then we start to think, like, what would it take to make it non-circular? Like if it were non-circular and just the entire shape of the part you wanted to extrude at once,
right?
What does the chemistry have to look like? Or how do the physics have to work out so that you can do that and still get the properties you wanted? And that kind of led us to, well, we're chemists. We can make the chemistry do things and behave in ways that no one else can do.
Sure.
And then can we use that to then build a process that does that thing where you just extrude the entire kind of cross section at a time?
What are the most important properties in the resin material that allow for this?
Yeah, it's properties. You're not talking about mechanical properties. You just mean like a feature of the resin.
Yeah.
So one of the things that we noticed is the way that So it's circular because when you're melting filament, for example, you need even heating to get a proper and thorough molten thing that you can then extrude.
Right.
But to get that evenly, it has to be circular, and then you're also limited by the speed at which you can achieve that kind of like heat penetration into your filament. So one of the things that we tried to do is, what if the heating and the way the to get this heat penetration into materials is done not by the machinery, but instead by the chemistry itself? How can we modify the chemistry to behave in a way that kind of mimics that behavior without us having to do anything? And so if then the heat to do that doesn't come from the machinery, then we can make that any shape, and we can still get that effect that we need. And so that started to think about that. That was like one way that we would think about it. So obviously for melting, it's kind of the opposite of so when you melt it, you then extrude it, and then it goes from hot to cold. In a thermoset, it goes from cold to hot, like a hot molded area. But what we really care about is phase gradient, right? It's you get the solid on the outside, and then the liquid on the inside, and that is still limited by the way the heat transfer works in your materials. And so we kind of found like a chemistry way to kind of cheat the way heat transfer is achieved. And so if we look at our resins too, it cures in ways that are also very unconventional. They don't really exist in nature. And so that's how we've been able to build these kind of ridiculous processes. What enables this process is not just the robot. Like anyone can build. I mean, building a robot is hard, but it's a solvable problem with tools that we have today. What's unique is the chemistry that behaves in the way that allows the robotics to manipulate it. Like, the robotics are just used to achieve the timing and the control, but it's the chemistry that makes it unique. In general, I think one thing that we've been talking about internally as a philosophy about the world is that we feel that every building material, like in the history of human building materials, are like naturally occurring materials. So it's like mud and straw, like a natural composite, or even cement and brick and mortar, cement and rebar, all this, like steel. Everything is like something we pulled out of the ground. And so to process it, to manufacture it, we have to do what the atoms tell us to do. Like we have to make the atoms happy so that they behave the way that we want them to.
Sure.
But we as chemists in these synthetic composite systems, we can actually make the chemistry do what we want it to do. Instead of us being bullied by the chemistry, we can kind of like make it do the hard work and then make manufacturing easy. So that's why we believe that composites should be the most scalable system, because we can define all the rules of how they should behave. Like today, in epoxy, we kind of treat it like it's a naturally occurring, operationally it's the same way. Like mud drying or an epoxy curing, we still have to do what the epoxy tells us to do. 80 degrees C for 3 hours, okay, fine. And so while these synthetic systems have that capability, no one's exploited it in a way that allows like these unconventional manufacturing methods. And I think we're the first to do that.
So where do you go from here? I mean, obviously, I know you probably talked to a lot of people out at JEC, and where do you see this initially, this technology being developed for?
Yeah, we originally designed this process, and you look at our RPE proposal, which the abstract is public, it was designed for wind blade manufacturing. So things that are very long, wide, very thick laminates, and structural. But what we realized is we can just think of a blade as like a prototypical infrastructural part. And so our ambitions have grown into things like construction and how do we make like a curved I-beam, or if we could produce at 20,000 kilograms an hour, if we had the manufacturing capability to do that, we wouldn't build stuff in a factory, ship it, and assemble it on site. We would just move the machine and build it on site. And that also enables the capabilities to do things like making a 1 mile long, 2 mile long I-beam or a span or whatever it is. And so that's our vision has grown with as the technology seems more real to us as well as we're building it. Our vision is there. But in the short term, it's also like it's just a custom manufacturing process that is mold free, and we can make these structural parts. So there are some limitations in kind of the feature sizes we can make, right? So 3D printing is great for making these intricate parts or internal trusses or whatever, but there are so many other things that require a very different approach to things to things like this. And so we're looking at, can we make custom boats, for example, or
Sure.
or one-off parts, furniture. These are things that will help us hone our skills and operate the machine, all this stuff as we get to these really large parts. But we've also thought about space. This machine is just one way that we implement the process. The core of the process is we can go very fast for an arbitrarily shaped nozzle, and we can put that, for example, on a 6-axis arm and treat it like a 3D printer. But instead of doing like a bead size that's cylindrical, it's ribbons, or and the ribbons can change shape as it's going, even if it's really small, or whatever you want to do. So there are different ways that we think about it. But we, in the next like 3 to 6 months, we are looking for people who need custom parts very quickly.
Yeah.
That are very, very strong.
Do you envision selling the chemistry?
I think ultimately, to be truly venture scalable, to change how we build the hugest things on a global scale, we probably do have to sell equipment and sell the chemistry that feeds the equipment. We can't operate all of it. But I do think that we have a better argument for becoming a contract manufacturer than, let's say, a 3D printing company. In general, I think because the throughputs of 3D printing can be quite low, it's very difficult to make that work as a manufacturing model. And so we see a lot of 3D printing companies and startups moving to selling machines. Our rates are so high already. And so what we focused on in the last few years is how do we get like the raw manufacturing horsepower, and then we can like finesse it later. Everyone else has been focused on getting like this super tight finesse, and it kind of pins them into ways that their manufacturing becomes unscalable. And so, for example, even right now, 16 months of work, and I would say our first prototype machine, we're at 200 kilograms an hour. And that is like the floor of our production. That's like, we're going extra slow now, and so that's already on the scale of the largest like 3D printers.
Right.
And we're producing parts that are much higher fiber volume fraction and higher quality. And the question then for us though is more like, we can't afford a sky crane right now, even though we can produce the parts that would require one. And so there's like other tooling that kind of limits us, but it's not the throughput. And so for us, we're trying to think about what exactly we have to really quantify to decimal points, kind of the unit economics, and figure out if that kind of manufacturing model will work longer for us than other companies. But we're still figuring it out.
Well, Dan, thanks so much for joining me today. And I do want to take you up and at some point get over to your facility, because I'd love to see some of this in motion. I've got your website pulled up. It's Perseus Materials. If any of our listeners want to check you out. Also had a little, I was going to play it earlier, but I forgot to. You got a presentation on YouTube, but it's real quick. I think it was kind of prepping for JEC, but probably the best way to get a hold of you or to learn more is to just go to the website, and I guess you guys will kind of feature updates as time goes on.
We will, and we have a little, in contact form, or you can just email me at dan@perseusmaterials.com.